The integral test is the final, when you get ratio test and it's L equal to 1, can't tell, this is the bomb you drop on the series so that you can see if that converges or not. The integral test has 3 criteria that you have to write. Remember the good times with ratio test? So many good times. That, all you needed were all terms positive. This one you have to add 2 more. Because it is an integral, you're going to have to add continuous and decreasing on the interval. If all the terms are positive, what does the final value have to go to converge? 0. So does it make sense that it's always decreasing? You don't have to prove this. Just write it down. But you could, if IB gave you like 12 marks, you could prove U of n plus 1 minus U of n that it's decreasing on the interval. Okay? We're not looking at these. We're looking at these. So if the integral from 1 to infinity converges, then the series converges. If the integral diverges, the series diverges. And I think I have the proof of it. You can look at it using the Riemann sums. You're welcome to look at those. There's 2, I think there were 2 proofs, but I'm actually going to just go to some examples here. So once you do this, you need to have the 3 criteria: positive terms, continuous decreasing on interval, and we're going to prove that from n equal to 2 to infinity, that this series is going to converge. Now let's write it out first, just so it makes a little sense. This is going to be equal to 2 over 2 times the natural log of 2. Then it's going to be plus 2 over 3 times the natural log of 3. Then it's 2 over 4, ln of 4, all the way to 2 over n ln of n. That's the series that we're looking at. Does it converge? Does it diverge? What do you think? How many think yes? How many say no way? How many of you don't know? Well, that's honest. Good. I like honest. All right, so here's what we're going to do. We're going to, after we've listed all terms positive, continuous, and decreasing on the interval, we're going to integrate from 2 to infinity of 2 over n ln of n dn. If it converges to a value like 4 or 4/3 or whatever, then we know it converges as well. This does not tell us what the sum is. Not a sum finder. Very important. And Kurt mentioned that on that problem that we were looking at. That's why this one doesn't work. This one here didn't work because this is not what the sum is. The sum is not k. What we're finding is just a convergent value to just verify that it's going to be a value. So here we go. Let's do this together. What do you want u to be? I like it. ln natural log of n. So what's du going to be? 1 over n dn. Do we have 1 over n dn? We do. So I'm going to move this 2 out here. So we're going to have 2 times the integral of du over u. And so what's that antiderivative of du over u? Natural log of u, which is the natural log of n. And this is going from 2 to infinity. Notice I didn't write it here in red because this part changes when you change your u ln to u. That changes the boundaries. But we don't care about doing that because we're switching back to n. So don't switch them twice. There's no reason to do it. So this is going to be equal to 2 natural log of the natural log of n going from 2 to infinity. So now we do our improper integral. That's why I had it on the last test because we're using it now. we're going to take the limit as n goes to infinity of 2 natural log of the natural log of n minus 2 ln of the natural log of 2. What does this thing go to? Ever so slowly. If this is infinity, what's the natural log of the natural log of infinity? No, still infinity, yeah. And whatever this is, don't care. This is going to go to infinity. So then you put your therefore statement, since all terms, what? Positive, and interval decreases and is continuous, and the integral from 2 to infinity of f of n dn diverges, then what? Then series diverges by integral test. What do you think? Not bad. Now that you did the ratio test, this one isn't too bad. Okay. And you can see this example, they have 1 over n squared plus 1, terms positive, decreasing on the interval. This is actually going to turn into an integral using arctangent. Going from 1 to infinity, you get pi over 2 minus arctangent of 1 is pi over 4. Pi over 2 minus pi over 4 is pi over 4. This is a converging value. Is this what the sum is? Nope, that is just, all that is that it verifies that this thing converges. And so therefore the series converges by the integral test. Okay, we talked about the p series. For 1 over n to the p, the sum, as n goes from 1 to infinity, if p is greater than 1, the series what? Which is it? It's if it's 1, 2, if it's like 1.1, 2, 3, 4, it's going to do what? Converge. And if it's less than 1, it's going to diverge. You remember those. And I'd even put another one here. The sum as n goes from 1 to infinity of n to the p. P is going to be what to converge this time? Turn to your neighbor. Tell them what they think. See what they think. So this is going to converge. P is going to be less than -1. The series is going to converge. Right? Because if this is negative, then it would put it down here, and then it's got to be less than that to get -2, -3, -4. And then P is going to be what? P is going to be what? Greater than or equal to? There you go. The series diverges. Good. And that's the integral test and tying into that. What's wrong with -1? What series is that? That almost killed Anne. Harmonic series, right? -1 over n. So it didn't for those out there. Okay, good. All right, so here's what you're going to do. You're going to determine whether these series converge or diverge, and you're going to use the integral test for them, and go ahead and work on those. And it's just a great little review for of integration. And all the answers are there. You start with number 1.